All right, good morning. We've worked a couple of problems, conservation of momentum with plastic collision, and then we worked a problem with an elastic collision. I want to work another example with a plastic collision, but in this particular case it's just a little bit more complex because not everything's zeroed out with one object or another. So here's an example of a toy car and a toy train. For example, so here we go. A 0.4 kilogram toy train moving forward at 3 meters per second collides with and sticks to a 0.8 kilogram toy car that is traveling in the opposite direction at negative 2 meters per second. What is the size and direction of the final velocity of the two cars? Okay, so neither object is stopped to start with, and neither object is stopped at the end. So we need to recognize a couple of key factors here and take that into account into our problem solving. So as always, we're going to start with a drawing, and this is where I wish I had one of those videos like on YouTube when people cook and they snap and the carrots are chopped or something like that, but I don't want to do that. So I'm just going to draw like a generic looking train object and a generic looking car object. Well, I've drawn them going opposite directions because the problem clearly says that they are going different directions. So that's the train and that's the car, and so we need to start defining some variables and some terms and some conventions. And as always, we're going to use up and to the right as positive and communicate that with our reader. Okay, so we're dealing with, of course, with a train, a toy train, and the car, toy car. Okay, of course, we're dealing with momentum, so we'll go ahead and define momentum. And that's mass times velocity. That means we have to make sure everyone understands that we're talking about mass is m and velocity is v. So we should always also we can use, last time we worked a problem, we said initial and final. Let's change it up a bit and say before and after. Same thing, different terms, just to maybe help you out in case you're looking at different solutions or different people are helping you and you're trying to figure stuff like this out. So I'm pretty sure we've got everything defined here, and we can keep all of that together, separate, and we can start talking about the individual objects. So we have to label everything, the mass of the train, okay, because we don't have to put before or after, do we? Because the mass of the train itself doesn't change, but we're going to talk about that in just a second. And that's a 0.4 kilogram. Mass of the car is 0.8 kilograms. The velocity of the train, 3 meters per second. And the velocity of the car is 2 meters per second. And it says negative, and it also says opposite direction. So that's just meaning sometimes it will say opposite direction and not have the negative sign. Sometimes it includes it. You just kind of have to be clear and understand it. And if you're communicating that in your solution, then you're going to be right. So the velocity of the car is 2 meters per second. And we can say to the right, to the left. We could always do stuff like that to be clear if we want it to be. Okay? So, but we're going to really deal with that in the signage of our problem. Okay? So we'll start with the basic principle of conservation of momentum. And say P before is equal to P after, right? Before and after the collision. One thing we want to start right now, though, on this one is look at the mass and say, this is a plastic collision, right? And so the mass after the collision or the momentum, the mass of the momentum, that's what we're talking about, is equal to the mass of the train plus the mass of the car. See how we're keeping all of our terms clear? And we're trying to find velocity after. Okay? That's really all we don't know. So we're looking for the velocity after. We want to expand this momentum term there and that momentum term there and put the values that we know in for that. Momentum before is just the mass of the train times the velocity of the train plus the mass of the car times the velocity of the car, and that's going to equal the mass afterwards times the velocity afterwards. Okay. Do we know any of these terms? Yes, we know all these terms except for that one. So all we're going to do is rearrange the equation. Velocity after is going to equal to the mass of the train, velocity of the train, plus the mass of the car, velocity of the car. All of that term divided by the mass after. And you can put parentheses around that to be clear and make sure you do that addition first. Okay? Very simple now. Mass of the train is 0.4 kilograms. Velocity of the train is 3 meters per second, plus the mass of the car, 0.8 kilograms, times the velocity of the car, and that's where that negative sign is going to come in, negative 2 meters per second. Okay. Now, you might say, oh, you forgot your sign up here. I wrote to the left, see? So see, you can handle that either way. Just as long as you're handling it there, and it's clear all the way through, and it's a negative there. And I'm going to go ahead and divide by the mass after. So what's the mass after? Mass of the train, 0.8 kilograms plus 0.4 kilograms. Now if we'll look, those kilograms are going to divide out through the entire problem. So all we have to do now is take our calculator, multiply 0.3 or 0.4 times 3, 0.8 times negative 2, and divide that by 1.2. When you do that, you will get an answer that says minus 0.333, of course that's repeating, meters per second. What does that really mean? So the velocity after is actually 0.333 meters per second to the left. And that makes sense because the weight of the car was more than the weight of the train by quite a bit, okay, in magnitude, and that makes it sensible that it would work out that way.